Hello again. Welcome back. So now we finally get to talk about sequences. So if you remember from the welcome video, I explained that the part of Calculus 2 that people remember as being the most difficult is almost always sequences in series. The reason, or at least part of the reason for that, is that the two words are really, well, they sound a lot alike. Sequence and series, right? The World Series is a sequence of games, right? In English, we use the words interchangeably. And so that causes a lot of confusion. The other part of the confusion is, in order to really understand this stuff, you just have to do a massive amount of homework to get good at it. And then people do okay. So what you typically see on exams over sequences and series is people who do really well and people who do really bad. And it's just a matter of doing enough homework to get really good at it. So let's jump right in and see what we're talking about here. So what's a sequence? Well, the formal definition that you'd see in a textbook, right, is that a sequence is a function whose domain is the natural numbers. In other words, the numbers 1, 2, 3, 4, 5, 6. Those are our domain. That's a great definition, and we'll fall back on that in just a second. But maybe a better informal definition, right, to sort of pound into our heads what a sequence really is. It's a list. That's what a sequence is. It's a list. There's a first thing in the list and a second thing and a third thing and so on. So keeping the idea of a sequence as a list in your head will help a lot when we introduce the idea of a series later, and we'll see that those are very different things, and having this sort of a simple definition will go a long way to keeping them straight. So sequence is a list. Now, the notation may look a little strange because I just said it was a function. This doesn't look like f of x. This looks like f sub n. And that's because we're thinking of this like a list, right? We really have a first thing, a second thing, a third thing. So this kind of notation with the weird parentheses and s sub n, what that means is there's an s sub 1, right? That's the first thing in the list. Then there's an s2, that's the second thing in the list. An s3, that'd be the third thing in the list. And everybody's getting really bored now. You see how the pattern would go. We usually would denote, if we want the whole sequence, we put parentheses around it, or sometimes little brackets, right? So that's what the notation of like a whole sequence would look like. If we need just a particular one, like the seventh thing in the sequence, we may call it like s sub 7, without the parentheses or the brackets. Okay, but if this is a function, and it is, we could fall back on that a little bit to draw a picture of a sequence in a way that maybe we're familiar with and used to seeing, because we could treat this, again, the domain is the natural numbers. So the first thing in the domain would be 1. I could plug 1 into the sequence and get out a y coordinate, or maybe a better way to think about that is I just plot the point at 1, comma, s1. So right there on the y-axis, that's where s1 lives. Okay? Then here's s2, and it lives about there on the y-axis. And s3 goes down here on the y-axis. And we could just keep drawing these pictures where we move things along, and they're just doing their business, right? They're all just showing up one after the other. And they're dipping below the axis there. Oh, here they come back. So as they go along, right, maybe an interesting question to ask at this point, and the main thing we're going to want to know about these sequences as we go along is, are they going anywhere, right? Are all these dots starting to get closer and closer to something? Right? In other words, in this picture, do we have a horizontal asymptote? Right? Are these dots all getting closer and closer to some limit that maybe we'll call S? If they are, then the picture would look kind of like we have, where the dots all get closer and closer to that purple line S. Here's another picture of what sequences might look like. This is the way I like to think of them. You can sort of imagine a number line, but now you can't tell from my picture which one is first and which one is second. So you have to kind of watch the time-lapse stuff here. So that was the first, second, third dots. There's the fourth one. Here's S sub 5. There's S sub 6. There's S sub 7. And they're just popping up on the number line. Right? And the question is, are they all sort of going somewhere? Is there a number that they're all aiming toward? And in this case, it looks like they're all kind of starting to cluster around some limit. It'd be about there, and that's what's happening in this example. The dots are all sort of heading to one point. What we'll see when we look at the homework is examples that look more like this. So here's a formula for our sequence, right? It was 1 over n. So if I was going to write that out term by term, right, then what I would get is, well, the first term would be 1 over 1, right? When n is 1, that's the very first thing in the sequence. So the first thing in my list is 1 over 1. Of course, that's just 1. Second thing in the list is 1 over 2. The third thing in the list would be 1 over 3. And the fourth thing would be 1 over 4, and so on. So if we look at that list of numbers, 1, a half, a third, a fourth, a fifth, you see they're getting smaller and smaller and smaller. And it's not too hard if you think about it to convince yourself that, you know, 6th, the 7th, and 8th, and 9th, those are all getting much smaller. They're going to 0, right? Of course, the idea here is that when n gets really big, 1 over a billion, then 1 over n is a billionth, right? This is always fun to say when you're in a face-to-face class because you have to take a step back so you don't spit on the people in the front row. So 1 over a billion is a billionth. So when you have a big number in the denominator, it makes the whole thing small. Okay? That idea will come up over and over and over through the rest of what we're going to be talking about. That what we need to look at when we have a formula like this is, well, is where the big numbers are. Are they in the numerator? Are they in the denominator? How do we tell? So the way we're going to do that is what I like to call the Tower of Power. This is really cool. It took a long time to get this to work out too in the animation. So this is also really cool. Look, just raise my tower there from the bottom to the top, brick by brick, having my peasants working on it to build my wizard Tower of Power. The kids play a lot of D&D. So here's my Tower of Power. And I have it labeled in a way to sort of help us remember which things are more powerful than others, which things get big faster than others. So, for example, let's start here in the middle, this brick, right? It's n. So how does n grow? Well, the sequence n looks like 1, then 2, then 3, then 4, then 5, and so on. So that's how it goes. N squared, well, it grows faster. It's more powerful. It gets bigger faster because n squared looks like 1, and then 2 squared, which would be 4, 3 squared would be 9, then 16, and 25, and 36. They got a lot bigger really fast. And of course, n to the fourth would be a lot bigger, a lot bigger even than that. Right? So 1 to the fourth, then 2 to the fourth power, 3 to the fourth power is already really big. And of course, the higher the exponent, the bigger that the numbers get in this list. The more quickly, right, that they get big. N to the fifth would be even bigger. Of course, I skipped n to the third because I can't list everything. N to the third would, of course, be between n to the second and n to the fourth. N to the 3.99 would be a little bit below n to the fourth, right? The bigger the power, the more powerful the function here. N to the seventh would be bigger, and so on. And then we get to exponential functions, like e to the n, or 3 to the n. Notice 3 to the n would be a little bit bigger than e to the n, because, remember, e is like 2.71 something. So 3 is a little bit bigger than 2.71 something. 4 to the n would be even bigger. 5 to the n would be even bigger. Of course, 2 to the n would be a little smaller than e to the n, but would still be bigger than n to any power, right? Any polynomial. As we keep going, right, the bigger the base, right, the more powerful the function. Till finally we get up here to this one that's n! Big exclamation point. That's not just a really, really excited n. That n is not an n that's trolling people on Twitter or something that's putting lots of exclamation points in. That n, of course, is n factorial. That means that, well, okay, here's a better way to say it. What would be 7 factorial? 7 factorial would be 7 times 6 times 5 times 4 times 3 times 2 times 1. Right? In other words, you start multiplying by the next smallest integer as you go down. 2 factorial will be 2 times 1. Sometimes it's a little confusing to people. We'll run across this later. Of course, 1 factorial should just be 1. But what's 0 factorial? You think, oh, well, that ought to be 0 or something, right? Actually, 0 factorial turns out to be 1. The reason it's defined that way is so all the formulas that you get when you do those silly probability problems about how many ways can you arrange people in a line so that Sam doesn't stand next to Fred and all this sort of stuff. All the formulas that you do for those kind of combinatorics and permutation and combination problems work is you need 0 factorial to be 1. We'll run across that a little later in the class. Anyway, what's bigger than an n factorial? Well, n to the n would be bigger than an n factorial, right? Because now I'm changing to both the base and the power. On the other hand, if we start looking in the basement, right, things smaller than n, well, that'd be things like a square root or a cube root or a fourth root. Again, as you make the power smaller, then we grow, we go off to infinity. I mean, n to the 1/4 power does get bigger and bigger and bigger and bigger as you plug bigger and bigger and bigger numbers into it. But the numbers get big kind of slowly, right? A lot slower, say, than square root of n or e to the n or n factorial. That's why it's all the way down here in the basement of our tower. And of course, down here at the very bottom, I've put in log of n, because that's remember, the inverse of e to the n. Log of n goes off to infinity too, but it goes really, really, really slowly. So it's not very powerful at all. And of course, there's smaller things even than log, like log of n, and so forth. But this is just some way maybe to visualize what functions are bigger than what other functions, which functions are more powerful. And the idea here is this: if the bottom of a fraction is more powerful, then the fraction is going to go to 0. We saw that a second ago, right? If you have a big number in the bottom compared to what's in the top, if the bottom is really big, so you have something like 1 over a billion, that's like a billionth, that's really small, the whole thing's close to 0. If the top is where all the power is, right? If the top is more powerful, then the fraction goes off to infinity. So if you have something like a billion over 1, that's like a billion, right? The top is more powerful, then the whole thing's getting really big and the whole fraction goes off to infinity. In case of pi, we break glass. No. In case of pi, this isn't like a fire alarm. In case of a tie, what we do is we break out the coefficients. In other words, we look at the coefficients, the number in front of the most powerful thing in the top and the bottom. Now, this definitely needs an example. So here's our example. We have a fraction, right? We have a 3n squared plus 4 on the top and a 5n squared minus 2n on the bottom. And we ask ourselves, who has the power in this situation, right? This is like a sociology question. But if we look at this, the most powerful thing in the top, right, is not the 4, because of course 4 is always just 4. It's the n squared. Because if n gets bigger and bigger and bigger, the 4 doesn't change, but the n squared does, right? So this would be like, 3 times a big number plus 4, like 3 billion and 4 or something. In the bottom, right, then where the power is in the n squared, not the n. Because again, compared to an n squared, an n is kind of puny and pitiful, right? So it just gets made fun of. People kick sand in its face when he goes to the beach. It's just really sad. So all that really matters in the bottom is the 5n squared, and all that really matters in the top is the 3n squared. So we're not going to do algebra and cancel them or anything, but what we are going to do is just look at those coefficients, because it's sort of like having 3n squared over 5n squared. We don't have exactly that, because again, we don't do the algebra to actually cancel it. But when the numbers get really big, this thing looks like 3 big number over 5 big number, which is roughly 3/5. All right, here's another example. So in this situation, we've changed the power in the top. So now it's 3n to the 4th plus 4. Okay? So now the power in the top, right? The most powerful thing there is n to the 4th. Again, the bottom is the same. So the power in the bottom is still all inside the n squared. So this is like an n to the 4th over an n squared. And of course, you can almost cancel those and just make the whole thing an n squared. We don't do that because we're not doing algebra. We're not canceling. We're just sort of saying that the top is way much bigger than the bottom, which means the whole thing diverges to infinity. And that's all we have to say. So if you've seen these kind of problems before, you may have been told to divide the top and the bottom by the highest powered thing or the highest powered term and this sort of stuff. And that's great. But the truth is, we're going to need to be able to do these kind of problems very quickly. We're going to need to be able to look at it, see what the answer is, and go on. So unless there are problems that require more work, like using L'Hopital's rule or something funny like that, we'll see examples of those in a later video. We can just look at this and just see what the answer is and go on. And if you need to explain on an exam why the answer is what it is, you can just say the most powerful thing in the top is n to the fourth, the most powerful thing in the bottom is n squared, the top wins, so it goes to infinity. In this example, right, we've changed up the bottom now, so it's 5n to the sixth. So it's bigger now in the bottom, so the power is all in the denominator. That means that the denominator wins, the whole thing goes to 0. It's just that easy. There's another example. 3 log of n plus 4 over n plus 5 square root of n. Okay, everybody's tired of listening to me read, but where's the power here? In the top, it's in the log. In the bottom, it's the n. And again, who wins, right? It's almost like playing poker or something. One person plays a log, the other person plays an n. Who wins? The n. Because remember, log is really low on our tower of power. So the bottom has all the power. The bottom's bigger. If the big number's in the bottom, the whole thing converges to 0. One more. Here's 5e to the n minus n over an n squared plus 2 square root of n. Well, of course, the most powerful thing here on the screen is the e to the n, and it's in the top, right? The top has an e to the n, the bottom has an n squared. The e to the n wins, and so this whole thing will diverge, we'll say, to infinity. Right? So if you remember our language from before, we talked about converging and diverging. Right? It's the same idea here. If a limit exists, we say it converges to that. Right? It might converge to 0, might converge to what did we have before? 3/5 is a number. If the limit doesn't exist, which can mean the limit maybe it's infinity, we would say that it diverges. Right? In this case, it's special. It diverges in a special way. It diverges by getting bigger and bigger and bigger, and we say it diverges to infinity. Okay? Let's look at one quick theorem that I think, if I didn't tell you, everyone would just assume it's true and not really worry about stating it, or why would anybody bother to say this? Because it's the sort of thing that you go, oh, obviously it must be true. And what I'm about to say is certainly true for limits of functions. So it's what everybody's used to doing with limits all the time anyway. So if you had two sequences, one of them we'll call Sn, and say it converges to S, see, so that the letters match. Then we have another sequence, T sub n, and say it converges to some T, again, so the letters kind of match. And we said, okay, what happens if we take the Sn and the Tn and we add them together? Well, if we take two sequences and they're both converging, we add them both together, then the sum will converge, of course, and you take the limit of each piece separately and then add those together. So the limit of Sn plus Tn should be the S plus the T. In other words, if you have limit of two things, right, you just look at each piece separately and then add the answer together at the end. And you always do this, right? Functions work this way and nobody even thinks about it. And so why bother to state it? Well, I'm a mathematician, and mathematicians, this is what we do, right? We figure out what the rules are. We state the rules very carefully so that everybody knows the rules of the game that we're playing here. So that's what I'm doing. Right? If you take a number and multiply that by a sequence, then the limit will just be the number times the limit. Right? The same thing for multiplying, same thing for dividing. You just have to be a little careful to make sure that you don't accidentally divide by 0. So we're assuming we're not dividing by 0. Otherwise, the rule for division works exactly the same way. Now, one theorem that we use for functions that pops into play here is not all that often, but there are a few times when this is helpful. It's the squeeze theorem. So suppose that we had three sequences. Okay? We have a small sequence, A sub n, a medium sequence, B sub n, and a bigger sequence, C sub n. Okay? Bigger than or equal to in all three cases there. And we know that the big sequence has a limit of L, and the little sequence has a limit of L. So what has to happen to the sequence in the middle? Well, that's why we call it the squeeze theorem. It gets squeezed so that it has the same limit. Okay? Okay, wow, that looks weird. This also really needs an example. So here's an example of the kind of thing that that will show up where we can use this. So suppose that I have a sequence a sub n, and it's trapped between 0, right? It's always the sequence is bigger than or equal to 0, or maybe it's always positive. Maybe that's just bigger than. Right? That'd still work. It's trapped between 0 and then this other sequence, 3 over log of n plus 2. Okay? Well, what do we do with that? Right? How can we use the squeeze theorem? Well, it's really trapped between two sequences. Now, the 0 doesn't necessarily look like a sequence, but we could make it be one by making a sequence that just a list that was just 0, 0, 0, right? The first term was 0, the second term was 0, the third term was 0, 0, 0, 0, 0, 0. It's a really boring sequence, but that's a sequence, right? And so the terms in my sequence, a sub n, they're trapped between 0 and between 3 over log of n plus 2. Well, what happens to the sequence 0, 0, 0, 0, 0? Well, okay, obviously its limit is 0, right? It's not only is it going to 0, it's already there, okay? What about 3 over log of n plus 2? Well, log from our tower of power, or log of n plus 2, the same way, that goes off to infinity, so the big thing is, well, we got to choose between the 3 and the log. Who wins? 3 doesn't go anywhere, it's just always 3. Log goes off to infinity, so the big number's in the denominator. The denominator wins, so that whole fraction, right, that whole sequence, the limit is going to be 0. So I've got a sequence a sub n that's trapped between two other sequences, 0 and 3 over log of n plus 2. Both of those, the smaller one and the bigger one, both go to 0. So a sub n is trapped too. It doesn't have anywhere to go. Its limit has to be 0 also.